Hello everyone, welcome to my channel Chemistry is Fun. In my previous video, I have discussed about states of matter. In that we have started the discussion on gaseous state. In gaseous state, we have already discussed about the gas laws, in which I have discussed in detail about Boyle's law. Boyle's law, which states that temperature remaining constant, the product of pressure and volume of a given mass of a gas is constant. This we have already seen. I have also discussed the mathematical expression about that. Now today we will be discussing about Charles' law. Charles' law also can be referred to as the law of volumes because it gives a detailed account of how a gas will expand if the temperature is increased. And conversely, we can also say that whenever there is a decrease in temperature, there will be a decrease in volume of the gas. So we can sum up that the Charles law gives a relationship between volume and temperature of a given mass of a gas at constant pressure. The pressure has to remain constant. Now we can take one example. Let's say there is 273 ml of a gas. This is a sample of a gas. The temperature is at 0 degree C. This gas is heated to 1 degree C. And in this case it is found that its volume increases by 1 ml. The increase in volume is 1 ml. Now, for each degree change of temperature, the volume of a sample of a gas will change by a fraction. What is the fraction? The fraction is 1 by 273 of its volume at 0 degree C. Means at 0 degree C, whatever its volume was, 273rd part of that will be the change. Now why this 273 number we are using? The reason being, we know whenever we have to convert degree C into Kelvin, you add 273, means degree C plus 273 gives Kelvin. So this number 273 is used. Also we know that absolute 0 is minus 273 degree C. So there is a variation in volume whenever there is an increase in temperature. This variation can be explained mathematically as well. Now, if V0 is the volume of the gas at 0 degree C, and when the temperature is increased by T degree, the new volume is denoted by Vt. So Vt is the new volume when the temperature is increased by T degree C. And V0 is the volume initially when the gas was at 0 degree C. Now mathematically how we can denote Vt? Vt is equal to V0 plus, as I stated, 273rd part, so V0 divided by 273 into T. That is the increase in temperature by T I told, so it is the increase by T degree C. So it is this T degree C. If we calculate, means here you see we can V0 is common, so we can take it out, so we get V0 into 1 plus T by 273. On further calculation we get this formula, Vt equal to V0 into 273 plus T by 273. For future reference we may be using this formula, so I label it as equation number 1. Now in Kelvin scale or absolute scale, the lower limit called absolute 0, and this corresponds to minus 273 degree C. Now it is found that at this temperature all molecular motions stop. Then the volume of the gas would become 0. at this time the volume of the gas will be 0. Means the gas either turns to liquid or solid state. So absolute zero can be stated as that temperature where at which no substance can exist in the gaseous state. Okay. Now if I represent that capital T as 273 plus T, that is T as I told you, small t. What is small t? Small t is the increase in temperature. Means the temperature of the given mass of gas is increased by this T degree C. T naught is 273. Then 273 plus T is capital T. On substituting these values in the equation I earlier got, which I referred to as equation number 1, we get Vt equal to V naught into T by T naught. I just substituted these values in equation number 1. I'll just show you once. This is the equation number 1. In this I put these values. We get a new equation. Vt equal to V naught into T by T naught. So if we just rearrange, we get Vt by T is equal to V naught by T naught. We can also state from here that this can be also expressed as V by T is constant. But here the condition remains, the pressure should be constant. Means the volume of a given amount of a gas at constant pressure will vary directly as its absolute temperature. So if we want to show it graphically, we will get a straight line graph. If we plot volume and temperature, we will be getting a straight line graph as you see here. Pressure remaining constant. So volume versus temperature at constant pressure, we get a straight line graph. It is passing through the origin. We get a straight line graph because as we have just seen, V by T is constant. So if there is an increase in V, there will be a similar increase in T, so that the ratio will be constant. Hence we get a straight line graph. Next we go to one more law, that is pressure temperature law. This law states that for volume remaining constant, the pressure of a given amount of gas increases or decreases by 1 by 273 of its pressure at 0 degree C per degree change of temperature. Means for every degree change of temperature, the increase or decrease will be 1 by 273 of the pressure which existed at 0 degree C for the gas sample. So here we say that Pt at the means pressure at the temperature T will be equal to P naught plus P naught into T by 273. Here again we can rearrange and we find that Pt equal to P naught into 273 plus T by 273. Now we already know that T73 plus small t was the means it's the T degree C by which the temperature was increased. T degree C, small t degree C by which the temperature is increased. So this 273 plus small t is represented as capital T. We have just seen before. So this whole equation corresponds to Pt equal to P naught into T by T naught. By rearranging, we can cross multiply, we get Pt by T equal to P naught by T naught. So we can say that at constant volume, P is directly proportional to T. Means at constant volume, the pressure of a given amount of a gas will be directly proportional to its absolute temperature. P is directly proportional to T. I hope you all could understand the concept I tried to explain today. Thanks for watching my video. Please subscribe to my channel. Thank you all for watching. Thank you.